the earlier work about qubits using this method. And finally, I show the result of our study and I show the relation between Qutrits and CFAs. So let's begin with our study, our parts. So quantum entanglement plays important role in quantum information and quantum computing. So to use quantum entanglement, whether a given state is entangled or not is so important question. However, another important question is how entangled a given state is. I'll explain this question by this example. These are well-known states of tripartite qubits, ZHZ state and double state. When you measure the leftmost single qubit of them, this ZHZ state will be changed to 000 and 111 with same probability. And these states are both not entangled. However, one of the results of the measurement of double state, namely this state, is still entangled. It shows their entanglement have something different probability. And this difference is explained by SLOCC equivalence. Let psi and phi be n-partite quantum systems, and their SLOCC equivalent means they can be converted to each other by LOCC with non-zero probability. And LOCC means local quantum operations and classical communication. It is equal to this condition. So they are SLOCC equivalent if and only if their invertible matrices arise such that they can be connected by tensor product of these matrices. So quantum entanglement is a property of whole quantum system, and LOCC does not include any whole quantum operation. So LOCC cannot create any quantum entanglement. So SLOCC equivalent classification can be regarded as classification by the property of their entanglement. These graphs show the SLOCC equivalent classes of tripartite qubits. And this arrow means they can be converted by SLOCC. And there are 6 SLOCC equivalent classes, but these 4 SLOCC equivalent classes can be rated from ZHZ state or double state by SLOCC. So these 2 classes are relatively important than these 4 classes. These states are called SLOCC maximal states. Then we focus on strongly SLOCC maximal state, which is also SLOCC maximal, and we also focus on strongly symmetric state, which is also symmetric state. And this is important because for these states we cannot consider about we do not pay attention for the place of their single system. And in this study, a state which satisfies these 2 conditions are called Frobenius state. In this study, we focus on SLOCC equivalent classes of these special states. To make it easy to understand, we express these states graphically. The correspondence between Frobenius states and commutative Frobenius algebra has been already known. Moreover, in qubit, SLOCC equivalent classes of Frobenius states of qubit is expressed graphically using the correspondence between them and correspondence between these classes and classes of CFA. This correspondence was given by them. However, this correspondence does not for the other dimensional quantum system, this correspondence has not been known yet. Then, in this study, we extend this method to a qtrit, which is a 3-dimensional quantum system, and expressed like this. So, using commutative Frobenius algebra, we showed graphical classification of SLOCC equivalent classes of Frobenius state in qubit. Now we begin to explain this method. A commutative Frobenius algebra, or simply called a CFA, is a 5-tuple defined on a symmetric monoidal category. A is an object of M, and the other 4 elements are nulls of M. The first 3 elements consist of symmetric monoidal on M, and A is a monoidal object, and mu is multiplication, and eta is a unit of them. And this E is the unit object of this symmetric monoidal category. Similarly, first and fourth and fifth elements construct symmetric comonoid on M. And this multiplication and co-multiplication satisfies this axiom. It is an example of CFA on a finite dimensional Fourier space. This is a CFA on C2. This equation is one of axioms of CFA. It is not so difficult to verify, and the other axioms hold. So, commutative Frobenius algebra is defined on symmetric monoidal category. So, we can express this algebra using graphical representation of symmetric monoidal category. In this representation, an object is expressed as line, and another is expressed as a box. We assume a flow from top to down, so we write domain of this arrow is an upper side as an input line, and codomain is written in lower side as a not output line. And an identity arrow is written as a line of its object, and composition is expressed as a vertical connection. This diagram shows a ZF. A tensor product is expressed by horizontal juxtaposition like this, and the unit object is expressed as by no line. And they are symmetric monoidal category, so this symmetric natural isomorphism is expressed as intersection. Then, using this representation, a CFA can be written graphically. Remember, domain and codomain of these 4 elements. They can be written as these graphs. However, because of these all wires express the same object A, we can omit this label A. And moreover, checking the number of input wires and output wires, we can distinguish these 4 elements. So, we can omit this label of box. Then, a CFA can be written by this simple graph notation. Using this notation, the axiom of CFA can be written like this. Remember, a CFA consists of symmetric monoid and symmetric monoid, which satisfy this axiom. Then, equations from 1 to 3 express the axioms of symmetric monoid. This is associative law, and unit law, and commutative law. Similarly, equations from 4 to 6 express the axiom of symmetric monoid. And equation 7 express the axiom of Frobenius algebra. Okay. The correspondence between CFAs and Frobenius states was given as this theorem. We can make a CFA using a Frobenius state, and we can also make Frobenius state using a CFA. It means we can make a Frobenius state. We can make a CFA from a Frobenius states. A CFA which is made from a Frobenius state is not uniquely determined. However, a Frobenius state which made from a CFA is determined uniquely. Then we made a CFA from a Frobenius state and made a Frobenius state using this CFA, it is equal to the original state. And this theorem holds on every dimensional quantum system. In qubit, the relation between SLOCC equivalent classes of Frobenius state and classes of CFA has already been known. As I said, there are only two SLOCC equivalent classes of Frobenius states in qubit. These are CFAs which made from one Frobenius state, but they belong to only one classes of CFA, not both. In this meaning, SLOCC equivalent classes of Frobenius state of qubits are characterized by graphically. Name these as the classes of CFA, named SCFA and SCFA. These two kinds of CFAs are defined using the loop. This loop means a composition of multiplication and co-multiplication. In an SCFA, this loop is equal to connected line. On the contrast, in an SCFA, this loop is equal to unconnected, a discrete line. Actually, this classification used the rank of this loop. Remember, this line means the identity arrow of symmetric monoid object. So, in SCFA, the rank of this equation is equal to dimension of this symmetric this quantum system. In SCFA, this means the rank is equal to 1. Remember, this unit is expressed as this unit means vector. So, and this circle means scalar, so it is not influenced to the rank of this equation. So, this equation means the rank is equal to 1. An example of SCFA is a CFA induced from a CFA ZHT state, and it can be easy to verify to this rank is equal to dimension. And this is an example of SCFA, and it can be verified to this rank is equal to 1. And this relation can be expressed by this theorem. And our Frobenius state is SLOCC equivalent to ZHT state if and only if there exists quantum effects such that they induce an SCFA. The same thing can be said between W state and an SCFA. By this theorem, two SLOCC equivalent classes of tripartite qubits can be characterized using this graphical expression of these classes of CFA. So, we move to explain the result of our study. Like qubit, we attempted to characterize SLOCC equivalent classes of three-dimensional Frobenius states using classes of CFA. Of course, we do not know the classes of CFA which correspondence to a three-dimensional Frobenius state. However, in Qtrit, not like qubit, SLOCC equivalent classes of Frobenius state is also not known. So, before we study this relation, we have to find the SLOCC equivalent classes of Frobenius state. This difference is because of the number of SLOCC equivalent classes. In this table, the first row shows the dimension of quantum systems, and second row shows the number of SLOCC equivalent classes of these quantum systems. Tripartite quantum systems. And in qubit, there are only 6 SLOCC equivalent classes, but in 3-dimensional or more higher dimensional system, quantum system, there are uncountably infinite classes. Then, this is one of the results of our study. This theorem shows there are classes which include Frobenius states. There are 3 classes which include Frobenius states, and the other classes do not include any Frobenius states. These 3 Frobenius states are representatives of these 3 classes.
How did you find that?
Hmm?
Well, the first one's quite logical, the other two look a bit
How to find it?
Yeah.
I don't enter the detail, but yeah. Yes. So it's but the proof of the theorem by term and is done by the case distinction. The representatives of SLOCC equivalent classes of tripartite Qutrits has already been known. So we use the requirements of Frobenius states and eliminate classes which do not satisfy these two conditions. Using the strong SLOCC maximality, we can eliminate many classes, but they are still uncountably infinite classes. However, by the strong symmetric condition, the number of classes decreases by 3, and they can get this theorem. And checking CFAs induce these 3 Frobenius states, we can verify that this state induced an SCFA, and this state induced a CFA. However, the last one induced a CFA, which are neither SCFA nor SCFA. So, to characterize it, we define a new kind of CFA named an intermediate special CFA. Yeah. It can easily to verify this one induced as this new kind of CFA. Actually, this definition uses the rank of this loop. It can be easy to verify by this example. This rank is equal to 2. Assume that dimension of quantum system is not equal to 1, and the left equation means the rank is not equal to their dimension, because this right side is discrete line. So this is the rank of this equation is equal to 1. So they are not invertible. And the right equation means their rank is not equal to 1. If the rank is equal to 1, this scalar must be equal to 0. Then in Qtrit, they are not dimension, it is equal to 3, and it is not equal to 1, so the rank of this loop is equal to 2. Via this definition, the similar theorem hold like qubit, hold on Qtrit. A Frobenius state is SLOCC equivalent to this state. If and only if there exist quantum effects such that they induce an SCFA. And same thing can be said is this state and SCFA, and this state and an SCFA. This theorem can be expressed like this. Watching this diagram, you may notice that there are CFAs which are neither SCFA nor SCFA nor ISFA like this. And like this. So we defined an ISCFA and show the correspondence between these 3 SLOCC equivalent classes and these 3 classes of CFA. However, it may be possible to another kind of CFA and like this, and using SCFA and SCFA and this new kind of CFA, it may be possible to characterize these Frobenius states. So, is our definition of ISCFA meaningful? It is so difficult to answer this question, but as the supporting evidence, we show that these classes satisfies some universality. In two-dimensional quantum system, it has been shown that some pair of an SCFA and an ACFA can construct every qubit with the help of single qubits. They can express every invariant matrices, and they can construct n plus one partite quantum qubits from n partite qubits. So, using these two properties, this universality can be proved. And the same thing can be true for an SCFA, an ACFA, and an ISFA. They can express every three-dimensional invariant matrices, and they can construct n plus one partite qutrits from n partite qutrits. So using these properties, they can construct every qubit with the help of single qubits. Then, so this is the summary of our study. We found 3 Frobenius states, and there are no other SLOCC equivalent classes which include any Frobenius state. And we defined a new kind of CFA named ISFA, and proved the correspondence between qubits and CFAs. And finally, we show the universality of these 3 kinds of CFA, which means they can construct every qubit with the help of single qubits. So, this is the end of my presentation. Thank you.
Questions?
Do you correct 3 or 4 slides, maybe? One with the 3 colored stacks?
Which one?
Yeah, this one. One more?
This one?
This one. So on the left-hand side you have the equivalence relation of SLOCC. You transfer that somehow to the right-hand side now, the non-graded sort of way.
That's right.
So on the left-hand side you have an equivalence relation, these 3 colored blocks.
Yeah.
Can you transfer that to the right-hand side in some way?
The way to this relation?
So for example, there's 2 things on the right being mapped to 1 on the left.
Yeah.
So on the
We
left,
say Frobenius states the relation, their relation between Frobenius states and CFA. Actually, this relation is determined by Frobenius states and some quantum effects. So there are multiple quantum effects. So, and by selecting these quantum effects, this correspondence between determined between.
these effects
The
are
quantum effects is actually the choice of cup to flip your one of your
But
outputs.
they're SLOCC equivalent, right?
Huh?
They're SLOCC equivalent, these 2 choices.
Yeah.
So I'm asking, can you do the same thing on the right-hand side without referring to SLOCC? Does that make sense? Maybe I'll ask you afterwards.
Yeah.
The question is,
So you showed that you have this ISFA as rank 2.
Yeah.
So the obvious question is, if you go to another dimension, do you find ICFAs with every rank?
Yeah, it may be. Yeah, it's this CFA may be appeared by higher dimensional CFA, and yeah, it may be.
Do you have any kind of conjecture about how many of these independent qubits are known? I mean, so for qubits you have 2, right?
Yeah.
And for qtrits you have 3.
Yeah.
Do you have any conjecture about how this continues, or?
Yeah. Yeah.
that's enough for a quarter.
If I use an analogy, these operators composing a co-product and a product, they appear in B groups, and if you Eulerian idempotents, which are related to Frobenius structures on the byte groups which you get there. So from this point of view, do you expect that
Yeah, sorry. Yeah. Okay.
So do you know how to get the Euler characteristic out of your composition of a coproduct?
Euler characteristic.
So this is, in lead theory, it's possible to have a Euler characteristic, and then these ranks should be related to the fundamental groups of the lead groups, lead algebras. Obviously,
Sorry about that.
Sorry. Later.
I can tell you later.
Another question? So maybe I have one which is related to what they say here. Is do you have here an abstract notion of rank with this kind of things? This is when you say the rank, it's the rank of the linear map which is behind. So you are in the case of the Hilbert spacing. You see of the matrices, okay? You are here. It's the rank of the matrix.
So yeah, this is the abstract version of rank.
Yes, but it goes for 4 and 5 and so on.
You know,
So we've had a bit of a look at up to dimension 5. The rank depends. So if you go to the diagram with the coloured blocks, was that one up or something?
Yeah.
Can you go forward again? Right, so this one. The rank of the CFA depends only on the multiplication that the monoid part of the Frobenius algebra. So not the particular Frobenius, like the particular Coupling cap you chose to get your co-multiplication, or however you formulate your Frobenius algebra for your monoid. The rank is independent of that. So the rank should depend only on your Frobenius state, I believe. And they haven't quite properly classified the different commutative Frobenius algebras we get in high dimensions. But up to dimension 5, certainly you get at least one of every rank with the loop of each rank, and more than one